curve using this kind of pattern. We don't store the actual height information, but we store these numbers and the corresponding frequency, for instance, 1t. Maybe let's use different frequency, 3t. So we store, intentionally I will change this to, it doesn't mean anything, but the 70 then. So we, instead of storing the actual height, we store these things, and these are called the spectrum. And using the spectrum, we can easily restore the data. How? Just assemble 5 times cosine 70, the usually frequency range, and then sine 3t times 6. So 5 and 6 are stored at appropriate frequency, then we can restore the data anytime. So this is the strategy that I mentioned repeatedly. If you don't have a question, I will now let you know what people really do using complex explanation. So the storing the data is a key issue, and assume that we somehow have some kind of data such as I will use my node so that we can use the same formula instead of different formula. Assume that A0, A1, A2 is the sample signal up to A n-1 is the sample signal. Sample signal is this. In other words, music, then it is the height or the pitch or something, and then these kind of things are sampled. Then instead of storing the actual signal, this is the actual signal, we want to store something called the spectrum. Right. Spectrum. Instead of storing actual signal A0 up to AN-1, we store A0 up to AN-1. But many of these are zeros. In most cases, many of these are zeros. Many zeros, but at some places, some kind of pitch. Then if you just browse it, you will see what the contribution is, where the biggest contribution is, right? Biggest contribution. In other words, for instance, the frequency is 0, frequency is 1, 2, 3, 4, and so on. For instance, 200, then 200 frequency has the biggest contribution. And then afterwards, like 405, and then after this 600. So you check where the contribution comes from by analyzing the spectrum. What I mean is this one. Once we do this thing, we will have, assume that this is 3, height 3, this is 6, this is 4, and this is 5. Then it's like this. 3 times cosine 5t, 6 times cosine 12t, and then 4 times cosine 21t, and then 5 times cosine 27t. So these are the interpretation. So at frequency 5, we have this. At frequency 12, we have this. At frequency 21, we have 4. At frequency 27, we have this. Do you follow me? So these are stored. These numbers are here. Actual graph of this is upstairs, right? So actual graph of this is upstairs. These numbers are here. So you should distinguish signal from the spectrum. They are two different things. This 3, 6, 4, 5 are not heights. These are coefficients in front of the matching frequency. The matching frequency is 1, 2, 3, 4, 5, right? 6, 7, and so on, and 12, and 21, and then 27. So this is the point you should get. Then after storing this thing, we can recover the signal by using the same, almost the same formula, right? Almost the same formula. So it's essentially from signal to spectrum, spectrum to signal, essentially use the same routine, almost the identical routine to recover or to obtain spectrum. We essentially use the same routine. So let's use the complex version. Complex version of the spectrum is this. Because we need to represent waves, we need both cosine and sine. So cosine 70 times, for instance, AN is necessary. And then I will use B7. Instead of just N, I will use B7. So we need both A7 and B7 because to represent waves, we need both sine and cosine. But it's very inconvenient to represent this way. So people decide to combine these things in complex number. How? Just C sub 7 e to the power of 7it will do it. Or 7I pi t, something like that, right? So we just adjust those things a little bit. And after this, I will use 2 times pi also, right? 2 times pi is typically added. But it doesn't matter. In any case, we do this kind of thing. So do you get it or not? Do you get it or not? We, instead of worrying about these kind of things, 2 times. I attach 2 times everywhere. So instead of worrying about 2 separate coefficients, we just mix the coefficients in complex coefficients. But essentially we need, for this thing we need B7 plus I, F7, right? Essentially we need 2 real parts. Then what is the advantage of this thing and what is the advantage of this thing? This thing is very straightforward, right? It's real. But formula-wise, not very beautiful. This is complex, so it's difficult, right? But formula-wise, very natural. So this is the biggest advantage. If it's complex, you don't need separate formulas. You just need one formula to handle the case. You get it? So this is the major reason why people use this thing. But recently, people use cosine or sine to do some kind of compression. Then let's do I will write the conversion. Assume that we have 1, 2, 3, 4 signal. This is a signal. Then what will be the spectrum? That might be a question, right? What will be a spectrum? I will show you in complex version. So to do it, we need the concrete formula. So I will show you the formula. So this is the formula. From signal, we can get this kind of entries in the spectrum by applying this thing. In other words, this AN comes in here, right? AN comes in here to determine capital AN appearing here, right? And vice versa. The other direction is almost identical. Take a look. As you can see, they are almost identical, right? They are almost identical. So I may take a snapshot of this thing so that I don't have to rewrite this thing on my own. Take a look. This is the case. So I will use this thing. For instance, assume the signal is given. 1, 2, 3, 4 signal is given. Then we will get spectrum. So I will calculate A0. A0 equals sum of these things from 0 to 3. And then W, I will check what W is later. W times K, K has to be 0, times N, and then AN. I just copy this verbatim. W to the power of 0 is 1, so it is A0 plus A1 plus A2 plus A3. So this is A0. So what is this number? 1 plus 2 plus 3 plus 4, which equals 10. Because of this, spectrum has first entry 10. Please calculate second and third on your own. I will let you know W. W is defined here, so I will graph this part. W is determined by this portion. So I will just write it. W is negative 2 pi I divided by the number of points, right? 2 pi, so 2 pi I divided by number of points. In this case, 4. So I copied W. So do you completely follow me what W is? Of course, in actual situation, N is not small like 4. N is like 10,000. More than, bigger than 10,000 is used. And later I will browse some pages to show you. Then, because of this, e to the power of minus pi I over 2 and e to the power of negative pi over 2 is cosine minus pi over 2 plus I sine minus pi over 2. Cosine pi over 2 is 0. I sine pi over 2, negative pi is minus I, so minus I is W. Do you get it? Minus I is W. So we get these ideas. And A1 equals, I will calculate A1. A1 equals, by the formula, I will write the formula in the summation form. W 1 times N, A-N. I will go up and show it. K happen to be, here K happen to be 1, right? K is 1. And then 1 is used, and then I just copy this portion. And then if I expand, but before expanding, I will handle W. W is negative I. Then 1 A0 minus I A1 minus 1 A2 plus I A3 is the result. If you don't understand, ask. Then this equals A0 is 1, right? A0 is 1, and then 2, and then 3, and then 4. So after this, we get 2I minus 2, right? Minus 2 plus 2I. So I calculated second value in the spectrum. So please calculate third and fourth on your own. Third and fourth on your own. I mean, yeah, index-wise, it is third and fourth one, but index-wise, it's capital A2 and then capital A sub 3. Capital A sub 2 and capital A sub 3. negative 2 coming from this, and then 2i coming from this. Please calculate capital A2 and A3 and let me know. So I completely calculated the spectrum. And then let's write the spectrum. Spectrum will be extracted. I made a mistake, sorry. I made a mistake. I somehow made a mistake. So let's extract the spectrum and then collect. So for the given signal, we can extract the spectrum, and spectrum is negative 2 minus 2i, or plus 2i, sorry. So this is the result, and if you have a question, ask me. So once signal is given, we can get the FFT result, which represents spectrum, and vice versa. From these things, we can assemble the signal. So let's assemble first value. Yes? Excuse me. Right. Then, it's very inconvenient to be cornered here, so I will use new space. Now, by using the spectrum formula, we can do this thing. Now, I want to restore. So now we have A0, A1, A2, and then A3. So we have these things. So from the spectrum, we want to restore the data. Then the formula that we need to use is this one. 1 over n happen to be 4, right? 1/4 sigma sum of k running from 0 to 3, and then w minus k, and then n, and then a k. Then it is 1/4, and then w, so I will write w to the power of something separately. W itself is given by e to the power of minus 2 pi I over 4, right? This is w. So w itself is calculated as minus I. Minus I is w. Now, minus w to the power of negative 1 is 1 over this one, right? Negative power means reciprocal. Then multiply I here, then we get I upstairs, and then I times this negative I is plus 1, so it is I. So w to the power of negative 1 is I. Do you follow me? So we can represent this way. W to the power of k minus k equals I to the power of k. So this will appear. So let's use this result to restore. So this represents an, and I will switch n and k here. I will switch n and k, the same formula, but I will switch n and k. Any questions? Just rewrote the formula with the specific value. Then, because of this, I will calculate many values. A0 equals 1/4, and then now n is replaced by 0. So I to the power of 0 is 1, so it is A1, A0, A1, A2, A3. Or if I write the summation form, k running from 0 to 3, and then this is replaced by 1, and then AK. Then 1/4, 10 plus minus 2 plus 2i minus 2. Why did I add I? Minus 2, and then minus 2 minus 2i. So we can cancel out plus 2i minus 2i, and then negative 6 subtracted from 10, so 4 over 4 or 1. Please restore the remaining signal. Please restore the remaining signal and let me know whether you completely restored the signal. So in MATLAB, we use this kind of command. Oh, yeah. We use this kind of command. So FFT can be done, and then inverse can be done. So I will use this kind of command to do the calculation. So let's do it. My signal is 1, 2, 3, 4. And spectrum, my spectrum equals FFT my signal. Do you understand what I'm doing now? We have a signal called my signal, and then we will do FFT and store the result in my spectrum. Then this is the spectrum that we hand calculated, but now as you can see, we can get the value, we can obtain the value. Take a look. We calculate this, hand calculate this value. We hand calculate this value. And then we hand calculate this value. We hand calculate this value. Do you get it? So once you have spectrum, and once you have signal, we can get a spectrum, and vice versa. Once you have spectrum, I will show you. So we have spectrum, right? My spectrum is here. Then we can do I inverse FFT to get to restore the signal, right? My spectrum is here, and you can restore the signal. Take a look. Initially, we used just real values, right? We used just real values, but in the spectrum, there was imaginary number, right? There were imaginary numbers. Take a look. My spectrum has imaginary numbers. Imaginary numbers. So this is the key point. We have signal, then signal became spectrum, but spectrum isn't necessarily real. It may have imaginary. Take a look. We have complex numbers. Somehow restored data is weird, right? So we are handling complex play completely. We don't have any guarantee that we have real when you use real signal, and we will have real restored value when you have real spectrum or something like that. There is no guarantee. Just complex numbers appear in both places or disappear. Then I will show you some example from the web. As you can see, assume that this is the signal. And somehow, we may record this height by sampling at many different points, right? At many different points, we can store this height. This is called the signal, right? But instead of storing this way, we calculate the spectrum. And then we sketch the spectrum. Spectrum looks like this. Then as you can see, can you see the peak? Can you see the peak? This is the peak, and roughly between frequency 100 and 150, right? About 120 hertz might be the case, right? About 120 hertz might be the major contribution, giving this kind of signal. right? Giving this kind of signal. Then, if you don't have enough space to store, you only store this height, right? This height, 0.9 something, and then this frequency. Then compression is done. Compression is done. Do you follow me or not? Of course, when you need more, when you have enough space to store, then second important thing can be stored, right? So like 5.2 about 3 is stored with corresponding frequencies such as 49 hertz. The 49 hertz and 5.3 might be stored. And if you have more space, then we may store about something like this or something like this, right? So like 3 hertz and then like a 0.36. Three things that we compress the data.
I mean, when you restore the signal, you're going to get kind of interpolated signal.
Right, interpolated signal that do not exactly match with the original one, but at least represent very nice. So there are two ways of recording music files, lossless or lossy. So sometimes if you store MP3 music on CD, the sound isn't great because there was some kind of loss. But if you use lossless option, then you don't lose anything there and get good quality sound. So mostly MP3 or some kind of WMA, many things have lossless storing method. Some Microsoft product has lossless way, then it is good to record on CD. We don't lose anything. So it's like this. We sample the data, assume that this is music, right? Music is stored this way, but we don't store this kind of height. We store only spectrum, right? But we don't store everything. We compress. So we somehow cut something below the threshold, right? Then we just store these frequencies and data. Then we later recover. How to do it? Change the file type. It could be MP3. It could be different thing, right? And once you create this kind of thing and patent it, and somehow it gains popularity, and Microsoft somehow uses it, you can sue Microsoft and then get like $2 billion. It really happened. Last year it really happened. Last year I cannot remember. So learn mathematics and make something and then patent it. So if you have a question, ask me. So you see the difference. So some people who don't attend class at all may suffer later because they don't know the difference between this graph and the other one. They think this is the same graph as the one and then have no interpretation idea of this kind. This is not actual signal. This is not actual signal. Do you completely follow me? It's not actual signal, it's spectrum. Actual signal is here. And you check best contribution and the next best contribution and so on. So assume that you want to do 90% compression. In other words, you just use 10% of space. Then among, for instance, 500 different frequencies, you just pick 50 best frequencies, right? First frequency, second best, third best, and then, right? So you pick 50 best frequencies. And then store the data, those 50 best frequencies. So that is one compression method. Yes? This is capital AN. These heights are, for instance, capital A0, A1, A3, A, for instance, 50, 49, A, 120 something. So these are capital A, and these things like A0 is negative 2 point, negative 1 point something. A, for instance, 5 is something. So I completely showed you the theory, hand calculation example, and MATLAB example calculation, and then actual graphs that we can see. When we increase the size n, capital N, we use small n for hand calculation, but if we increase the size, it will be different. So to check it, I will show you an interesting example. In the first place, only one contribution. Assume that you run sine 10t. Then only contribution comes from frequency 10, right? So I will use that kind of example. How can I sample 10 points of sine t? How can I do it? I do not know. So in MATLAB, how can I get 10 values of sine? T equals 1 at 0 to 1, right? And then sine t will do it. That's good. So let's store this data as signal, right? My signal is sine t. I will change t one more time. T should increase, right? So I will use t from 0 to pi, and increment is pi over 1,000. 2 times pi. So this is my t. And then my signal is sine t. Do you follow me? My signal is this. So how to plot it? How do I plot this thing? Is this correct? Easy plot, and then what? Just signal? What is the command? Just plot and so this is my plot. And as you can see, only contribution comes from sine t, right? 1. So let's check whether it really happens this way. So to do it, I will now do FFT. So spectrum is FFT of signal. So I did the FFT. Now I will plot this thing. What is the name of the previous one? Signal? Strange. Signal is not spec. Did I use spec? Take a look. So only contribution comes from about like 2 pi, right? 2 pi, right? 2 pi times 1, frequency 1, right? 2 pi. So in this case, if I want to compress, all I need to do is using frequency 1 or 2 pi, right? 2 pi. That's stored. All others are useless. Yes? Right. So if you want to compress this thing, then like among possible like 2,000 like frequencies, you pick one. Then percentage is like 0. What? 2? Less than 1%, right? You use just less than 1% of storage to store this signal. In any case, this is an example. So when you let's do many things. So I will create different spectrum coming from sine of 5 times t. Will this work or not? Plus cosine of 7 times t minus, I will use different coefficient, 10 times. Oh, I see. This should be the signal, right? And then after signal is obtained, we will do spectrum. So let's just stop here, right? And then I got it. Then spectrum is FFT of my signal, right? Then let's plot the spectrum. What is the problem? Did you see the problem? So you have different values, right? You have different. So in any case, we can do these kind of things to analyze the shapes, but I'm not good at MATLAB. So as you saw, you may try and check how to really implement all the things, right? FFT gives something, and then you get. But in any case, you should completely distinguish the signal from the spectrum. You should not mix these things and regard these the same. No, completely different things, right? These two are completely different. And the spectrum analysis means checking coefficients. Signal analysis means checking the height. Yes?
I'm not sure I see where when we get the spectrum, in a number of cases we're going to have some complex values. I'm not sure I understand where those complex values are used in the spectrum. I guess when we converted the sine and cosine functions take care of that. Where do I see, where do I use complex values in the plot?
The plot I just showed you isn't a great plot. In real situation, we should have imaginary plot and real plot, two separate plots. I just try to show you something, so that's the reason why we don't get real thing. But plot for real part and plot for imaginary part should be separately presented, and then any contribution in either place may be significant. You should not just ignore imaginary signal, imaginary spectrum, I mean. Do you know what I mean? So both imaginary and real part appear. So we need, in fact, two cases of spectrum. Real part spectrum, imaginary part spectrum.
So the plot is basically
The imaginary part, that's the reason why we don't get really nice thing. Because sine, cosine combination will create that kind of difference. If you just one function, cosine or sine, then either imaginary or real thing happen. But in the case that I gave you, I used both cosine and sine. That's the reason why imaginary appeared and then create that. No. In my opinion, no. I simply do not know how to do it. But it shouldn't be difficult. No, we create two separate plots. Usually we have the X range representing frequency. Frequency is real. And then spectrum, in imaginary real part is real, so it is two-dimensional. And then the same thing, frequency, and then imaginary spectrum also real, written in real. Essentially two figures will do it. So in real situation, so I will really sketch the case that we did. We had this kind of spectrum. We had 10 minus 2 plus 2i, and then minus 2, and then 2 or minus 2 minus 2i. We had this thing. And now we will have spectrum. It's real part spectrum, and then imaginary part spectrum. Real part spectrum has frequency 0, frequency 1, frequency 2, frequency 3, right? The same thing, frequency 0, frequency 1, frequency 2, frequency 3. Do you follow me? And then frequency 0 has 10. Frequency 1 has negative 2. I will raise this portion. erase this portion. And then negative 2 here, and then 0 here, and then negative 2 here. So this is the real part spectrum. So I will use this thing. 10, negative 2, 0, negative 2. So I extracted this portion. Do you follow me? So this is the real spectrum. And imaginary spectrum, yes? Oh, thank you, negative 2. And here, I will also raise this thing, but we may need to. So in a real situation, you should see both real and imaginary spectrum to determine. So let's do it. At 0, imaginary part is 0. Right? At 0, imaginary part is 0. At 1, at frequency 1, imaginary part is 2. At 3, 0. At this, so you should have two figures, right? Two different graphs representing both real and imaginary. Then you don't know where the contribution may come, because usually one means cosine, the other means sine, right? Cosine contribution, sine contribution. So please browse the idea and let me know. In other words, you should not just ignore imaginary thing like MATLAB did, because we didn't know how to call it. MATLAB just ignored the imaginary and then sketched the real part, right? But we cannot do that. In spectrum analysis, we should both honor imaginary and real, right? And then check what is going on in either place. Do you completely follow me or not? Yes? Something like that, but it is not an exact match because it's discrete. It's not real continuous. If we use interval and it becomes continuous, then we can really match term by term, but this is just imitating. So both imaginary and real should be analyzed, and then check anywhere we can get peak. We can get peaks. So I will pause and you may check whether you completely understand the idea or not. If you have difficulties, let me know. Real part of the spectrum.
Right. And if you were to reconstruct it in terms of the sine and cosine, that's the amplitude of the coefficient on the sine.
Roughly, that is the match, roughly, but we should return back to the formula to really form. Why? This is the reason. I will let you know the reason. Once we change the function into complex function, you don't see the contribution directly. It's not direct matching. Assume that you see 5 cosine t plus 7 sine 7t, then you clearly see the contribution, 5 and 7. But once you use complex numbers, it's different. For instance, 1 plus I e to the power of 7t, 7it, right? 7it. Then what happens is this thing, 1 plus I, and then this can be rewritten cosine 7t plus I sine 7t. Then, as you can see, cosine 7t here, and then minus sine 7t here, and then I times sine 7t plus cosine 7t. So as you can see, the contribution is not clear because of I involved. You follow me? So once we change it to complex numbers, we cannot just say, oh, this represents sine, this represents, we cannot say that. Do you get it or not? You cannot say, oh, you cannot say one contributes for sine 70, and then one here contributes for cosine. You cannot say that. As you can see, there can be different contribution. Do you follow me or not? So you cannot just read the imaginary part or real part of the spectrum and then say, oh, this should be cosine, this should be sine. You cannot say that, as you can see. Once we convert it to the spectrum, then something happens. But we should not ignore imaginary part. That's the point.
Back to spectrum, and you said based on the height of that spectrum,
Mm-hmm.
you determine which one to use.
Mm-hmm.
Can you have both real and imaginary? How do you determine which one?
So usually good idea is norm of the complex number. That is determined by this simple formula. Once we have a plus bi, then the norm of a plus bi is generally square root of a squared plus b squared.
Do you add that to the real part then?
No. What I mean is this thing. Assume that you have the spectrum at the same frequency like this. So you have frequency 77. At this point, you have like something like 0.5, and then this is a real spectrum. And then imaginary spectrum is here. And then at the same frequency, you have like a 0.3. Then what is the contribution? Then the contribution at 77 frequency is square root of 0.5 squared plus 0.3 squared. So this is the way you check what contributes biggest. Do you follow me or not? If you don't, then ask me. To check the contribution, you should check both real and imaginary result together. Of course, MATLAB itself handles it in some a plus bi form directly, but many programs separate real and imaginary. Maple especially completely separate real and imaginary part. A lot of packages also separate. So you should understand the meaning of spectrum for real part and imaginary part. Both are significantly important, and you cannot directly say, oh, this is for cosine, sine. You cannot directly say. Yes? Mm-hmm. Uh-huh. 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 Oh, great, thank you. That is a good idea. Then we can get the real part figure and then the graph, and then imaginary part graph of the spectrum. So let's return and then plot this thing with real, right? And then? Imaginary spectrum, right? In any case, we can use this to create something. But in this course, we are not handling commercial things. We are studying theories. And once we have formed theories, we may study further to even make something later. So I will review what we have studied. And then if you have a question, ask me. Once we have signal, we can get the spectrum by applying the formula, right? Once you have spectrum, we can use the formula to restore the data. We can restore the data like this, 1 to 3. I assigned this thing, right? And then now we want to analyze the spectrum, and the spectrum can be represented by two graphs, right? Two separate graphs. One representing real, the other representing imaginary spectrum. We cannot ignore imaginary spectrum. We should use both, and then check what kind of things may contribute, at what frequency. And then finally, assume that you are asked to check the biggest contribution, then the way is finding the norm of a plus bi generally, a squared plus b squared with square root. At the same frequency, for instance, 77, we have two different things, and we square and square. In negative, also squared means it may have significant contribution. But we cannot directly say, oh, real part contributes for cosine, imaginary part contributes for sine. You cannot directly say it, because once we mix complex and then complex number and functions, one does not just mean cosine, I does not just mean sine, as you can see here, right? It may contribute in different directions. So I completely summarized and showed you, and I will give you the matrix version very soon, unless you stop me here or ask more questions. Then let's go to the matrix version. And this is the key to make it fast. Without matrix version, it's impossible to make it fast. But with matrix version, it's possible to make it fast. So to get AK, we used this formula. And this formula can be written in matrix form. So let's do it. In matrix form, we can write these kind of things using capital A0, A1, A2, and so on, right? AN minus 1, right? And then this portion can be written here. And then we can write this portion, A0, A1, and so on, right? So we can write the summation in matrix form. And then this matrix has a pattern. And instead of writing the matrix on my own, I will show you. I will pause and then go to the summary and show you the matrix form. So we can write this kind of conversion in the matrix form, right? Capital A column is determined by matrix multiplied by lowercase, right? Matrix form. And as you can see, this is very systematic part, right? Because of this systematic part, right, the very regular part, people analyzed the method of speeding up the calculation, speeding up this multiplication. And they were successful. And many people say this. I heard this about the beginning of this year. Really, literally. So they speed up so much, it is insanely fast. So give me data within split second, you can completely do the effort. This is the reason why we are using these things in broadcasting, cell phone, everything. On and then log about n is a test. So not n squared, but order of n and then about log n is a test. So theorists want to improve those kind of things, but already insanely fast. In any case, people somehow manipulate this portion to speed up, and then they were successful. And then I will browse the web with you. We have showing at least one example. where is the, do you see, oh yeah, here. So you can download this algorithm and then modify and use. It's very fast. So roughly, I covered all the necessary part, and application is not seriously considered in this course. I just give you some ideas of using some compression idea or creating spectrum and then restoring data. But these are used to solve differential equations, not just differential equations, transmitting data. Why? Instead of sending the actual signal, we just send the spectrum, right? And then once spectrum is caught, then we restore the data very fast. So in the past, I was wondering why sometimes broadcasting companies use two different channels. One broadcasting the image part, screen part, the other broadcasting the sound part. Sound and screen part, image, cannot be mixed, and then we cannot do spectral FFT of sound and image mixture. If we do that, it's bad. That's the reason why we do the spectrum of image part and then sound part separately and then broadcast differently. But sometimes there is a mismatch, right? Then we have some kind of bad result. I do not know how people somehow handle that problem. Now, do you have any idea how companies, broadcasting companies or companies handle image sound problem? First, in film, they record both the image and then sound together, right? Then just they can read it simultaneously, so there is no mismatch, right? But in broadcasting, we cannot send the signal of sound and image together. Of course, they can send like side by side. That can be considered too, but that may be very inefficient. So you may develop your own prototype and a patent. And if Microsoft uses, you become a billionaire, right? I do not know yet. There might be some prototypes just sending both image and signal somehow synchronously, not separately. I do not. Mm-hmm. Mm-hmm. Yes. That's right.
So you're wondering why, how can you synchronize them?
You're right, without any bad situation happening. So roughly, once we do spectrum, we once create spectrum of image, it's nice. Once you create the spectrum of sound, it's nice. But we cannot mix and then make universal spectrum. It's bad. People store this thing separately, and then do some strange thing. But I do not know what prototype is now. But if there is no good prototype, you may develop it. So I do not know. If nobody did nice thing, then you may become millionaires, right? Multi-millionaire. Time. But problem is this: broadcasting, right? Telecommunication cannot synchronize all the time, right? It comes differently, right? Then then that's the case. And how can you really overcome that kind of problem? In any case, this kind of thing is very hot area, and knowing this is important. So in this course, we are not really handling commercial one, but we are handling the basic theory. And once you know the theory, you can learn more and more, and then even develop your own thing, especially how to mix sound and right audio and video together. Then it will be great if you determine your prototype is used by many people. Who knows? Now, the next thing is using these things in interpolation. Okay? Using these things in interpolation, and let's do it. So this is the formula that we can use. Use the relation x equals 2 pi n over uppercase n. Then we can convert the inverse FFT into this form. So we change the W part in this path. So take a look. When you see W part in the formula, you saw something like this, but now this part is replaced by X. Then it becomes continuous instead of discrete, right? We are handling now a function instead of discrete numbers. Do you follow me or not? I will return back to W. So take a look. In the past, in AN restoring, we saw these kind of things, right? We saw these kind of things with W. But now, W part having this thing is replaced by X, right? So now X restore this portion, and now instead of numbers, it's a function. So this is used to interpolate. So we do FFT to obtain uppercase A sub something, right? A sub k. And then after getting these things, we interpolate the function itself by attaching exponential function of this thing with x instead of discrete numbers. So this is the way we interpolate using FFT. Usually FFT itself is discrete to discrete, right? Discrete signal became discrete spectrum. Discrete spectrum becomes discrete signal, right? But now, discrete signal became discrete spectrum. Now, when you restore discrete spectrum, creates continuous function. This is the way we create the interpolation function. So please browse it and let me know. Mm-hmm. No. What I mean is this thing. If you follow all the steps, and then in W you will see this thing in W representation, and then replace this thing by X, then you can get this thing. So we can do the interpolation. Then how? For instance, this is the situation. Assume that you have, usually when you use FFT, we don't care about X coordinate. Usually it is 0, frequency 1, frequency 2, up to frequency n minus, right? So we don't even care about this portion. We assume this thing when you use FFT. So that the only thing that you worry is Y information, right? Y information. So these are written in terms of A0, A1, A2, A3, and so on, right? Then assume that you are asked to interpolate this kind of portion, right? This kind of points, right? These kind of points. Then all you need to do is finding the capital A, meaning spectrum. And then after getting the spectrum, you create this function. Then it's the interpolation function. Let's take a break until 3 p.m. by this clock and resume at 3. If you didn't receive, please come and receive the exam result.